What is an analog to digital converter, ADC? Imagine trying to listen to a song on a radio that only plays in static. To enjoy the music clearly, you need a device that can turn that static into something your digital music player can understand. That device is called an analog to digital converter, or ADC for short. It is a key part of many electronic systems, especially when microcontrollers need to read real-world signals like temperature, light, or sound. An ADC takes a continuous analog signal, which can be any voltage or current that changes smoothly over time, and turns it into a series of numbers that a computer or microcontroller can process. Think of it like translating a flowing river into a series of snapshots. Each snapshot captures the river's height at a specific moment, and these measurements are then converted into digital numbers. The process of converting involves three main steps. First is sampling. The ADC measures the analog signal at regular intervals, called the sampling rate. If the signal has high-frequency components, the sampling rate must be at least twice that frequency to avoid losing information. This rule is called the Nyquist-Shannon theorem. Next is quantization, where each sampled value is rounded to the nearest level within a set of discrete steps. The number of levels depends on the resolution of the ADC, which is usually given in bits. For example, an 8-bit ADC can representing 256 different levels. Quantization introduces a tiny amount of error called quantization noise, but it is usually very small. The final step is encoding, where the quantized level is converted into a binary number that the microcontroller or digital system can understand. ADCs come in different types, each suited for specific tasks. Some are fast but less precise, like flash converters, while others are slower but more accurate, like sigma-delta converters. The choice depends on what you need in terms of speed, resolution, power use, and complexity. In embedded systems, ADCs are often built into the microcontroller as part of a mixed signal chip. This makes it easy to connect sensors like thermometers, light sensors, or microphones directly to the microcontroller for processing. In practical applications, ADCs are everywhere. They help read temperature sensors in climate control systems, convert sound into digital audio signals, or interpret signals from touchscreens. When selecting an ADC, you want to consider how many bits of resolution you need, how fast it must sample, the voltage range it can handle, and how much power it consumes. All these factors ensure the ADC fits your project's needs. In summary, an ADC is a bridge between the analog world and digital electronics. It takes real-world signals that change smoothly and turns them into numbers that microcontrollers can analyze and respond to. This process is fundamental for making embedded systems interact with their environment, whether it's measuring temperature, capturing sound, or reading light levels.